Okay.
Okay.
Now, whenever I'm sizing the LV cable, I will consider two things. One is the rated current and second one is the voltage drop. I will avoid the fault level condition. The reason I will tell later. Okay, so two things I should take. For the ST cable sizing, I will take the current and the fault level. Remember, whenever the word fault level is coming, we have to determine the minimum cross section. Okay, my means my cable should be able to provide that cross section. Okay, so I am sizing the LV cable. I'm just assuming the example of 50 kilowatt motor. So the current you can determine easily √3 VI cos phi. Okay, so 81.8 is the current requirement. The meaning of this is my motor wants this current, correct? So
Yes.
in any condition, my cable should be able to supply this current. Okay, but as I told that suppose I am selecting a cable which can carry 100 ampere as per this load current requirement, but because of the derating, its current will change. So derating is nothing but the conditions. So I am assuming that this cable is laid overhead. So the two factor will be available: air temperature and the group rating factor. Correct? So
Yes.
these two factor will be applicable because it's a overhead condition. So I will go to the catalog of the vendor. Remember, try to size the cable from the vendor catalog because IEC is not manufacturing the cable. It is only providing the recommendation. Its value cannot be less than this. If you will size from the vendor catalog, you will size more accurately. Okay. So my suggestion is size from the vendor catalog. Okay. If you are not having vendor catalog, then only you should prefer this. Okay. IC is only the recommendation. It's not the cables are manufactured by the cable manufacturer, not by the IC standard. But they will follow the IC standard. Okay. Now the first factor is the ambient air temperature. I am assuming that my ambient temperature is 50 degrees centigrade. So the corresponding rating factor available is 0.8. Correct? Clear?
Yes.
Now this is the rating factor. Now I'm coming to the no other factor will be applicable. So as per my experience, I know that okay, the second factor is the group rating. Group rating means I am not using a single cable, I'm using multiple cables in the plant. So because of that, the group rating will arise. So I will go to the group rating. As per my experience, I know that the cable will be 3 core for this 50 kilowatt. So as I have discussed earlier as well that I will use the factor C because if I use this, I can lay my cable in the touching formation. So because of that, my support structure requirement and the width of the tray will reduce. So as no data is available right now, so I am assuming that there are 3 cables tray entire and each tray is having 9 number of cables. If we are having any data, just use the corresponding data. Okay, I am assuming that one is ST cable, one is LV cable, and third, third is the instrumentation. So this is the minimum condition I am assuming. Okay, so 0.68. Okay, so 0.68 I have used here. Overall rating factor will be the multiplication of the rating factor plus group rating factor. Okay, so it is coming 0.54. The meaning of this is, suppose I am selecting a cable. As per this, suppose I am selecting a cable which can carry 100 ampere. But because of that derating, that cable will carry only 100 into 0.54. Means that cable will carry only 54 ampere. So means that will not basically satisfy the criteria. Okay. So what I am doing here, I am just dividing the current with the derivative factor. So I will select the cable which can carry 151 ampere. Okay. This part is clear.
Okay.
But basically, instead of multiplying, I am dividing with the current. So I will select the cable which can carry 151 ampere. So my current, suppose my cable is copper and it is a motor feeder. So definitely 3 core cable will be there. So I will go to the catalog. This is 4 core. This is 4 core aluminum. This is 3.5 core. 3 core copper. This is armored. Okay. My cable is laying overhead. So in air, current rating will be applicable. So my requirement is 151. So it will come here, right? 165 will satisfy the criteria, correct? 135 is the lower current. 160, my requirement is 151. So definitely I can take 165, and this is applicable for the 70 square m cable, correct? 70 square m copper cable. So as per my first step, I can
Sir,
tell that
where how we will choose core of the cable? Like say for example.
it's a motor feeder, so definitely there is no neutral, right? R by B.
Yes, yes, okay.
If it is single phase, then two core, phase and neutral.
Yes, okay.
If it is a power feeder, then R by B and three phase
Okay,
power
okay.
feeder.
Yes,
So
okay.
like that we can select. We should know the load configuration.
Okay. How about four core? In which cases we will use four core cable?
Four core, if your neutral is full. See, if your
Means what
system is
does it mean?
having more harmonics, then
Acha,
you
okay.
should choose four core.
For example, in one of our sites, our team will use four core cables where dewatering is there. Like dewatering pumps of somewhere around 100 HP pumps are being used. Multiple 100 HP pumps are being used.
For the pump, you are using four core.
Yes, four core they're using. Why? In what cases generally they use? I don't know
You
the
are
reason.
telling for the motor feeder, you have used four core.
Dewatering
Hello?
pumps.
Whatever. So you are using for the
It's
pump
not possible.
application. See, if that
Means fourth core is used as a ground.
yes, fourth
Yes,
core
sir.
will be the ground in that case. Okay. That is not the
Okay,
phase,
right.
that is not the neutral
Okay.
conduct. That is the
Maybe you are right that harmonics
no,
might
no.
be.
No. In the motor, it is not possible to have neutral. Okay, so that will be the earthing core only, because it is not possible to ground that dewatering pump. Okay, so
Okay.
I am using the core in that case
Yeah.
for
Actually,
the grounding
they are
purpose.
using that cable for taking supply to the dewatering motor.
Yes, that's why I am telling it's for the body earthing. Okay,
Okay.
it's not the current.
Okay.
It's not for the supplying the current.
Yeah. Okay. It is for earthing only purely.
Yes, only earthing.
Okay, sir. Hello. I have two questions.
Boliye.
One is for lighting load. We have normally we use four core cable for lighting because neutral load is
See,
higher.
it's a four core means are you talk देखो
बोलिए.
Lighting loads, you are talking after the lighting fixture and after the panel, are you talking like that?
No, after the lighting panel to no, sorry, home substation to lighting panel. Sometimes
From substation to
normally four core
panel.
means normally four core means the lower side, four core 16, four core 25.
I am asking something else. Basically, you are telling from the PCC panel to the lighting distribution panel, right? This you are telling.
Yes.
Oh, definitely it will be for, see, basically for the light load, we are assuming that it is not possible to have the balance system because lighting can be unbalanced. So in that case, in the neutral current will not be 50%. So that's why we are just increasing the neutral conductor size.
No, my question is when to use four core cable and when to use 3.5 cable for lighting.
Dekho, if you are using the lighting transformer.
Yeah,
okay.
Normally we have used in industry light transformer.
Lighting transformer, then in the secondary, then in the primary of the transformer, it will be 3 core.
Yeah.
Okay, and in the secondary, it will be 4 core.
Yeah.
If you are able to balance your system perfectly, then I will suggest you to do 3.5 core. But for the lighting, you can consider 4 core. Okay. Because if you are able to completely balance or because balance means neutral will not have too much current. If your system is unbalanced, that unbalance will flow from the neutral. So because of that, your basically cross-section requirement for the neutral will increase. So that's why my suggestion is you can take 4 core if your client is telling, but 3.5 core can also be used if your system is balanced.
So wherever the system is having more unbalanced currents, there we will prefer 4 core. 4 core. If it is a little bit
harmonics
balanced
as well, if your system is having harmonics as well, because these things flow from the neutral only.
Okay.
So in that case, we should use 4 core or 3.5 core.
Sir,
Okay.
another
got it.
question is there. In industry, normally when motor inputs are two cables, means two core, two run 3 and a 185 square mm cable. But in sometimes there will be some fault. If some faults occur, can I use single one cable as three core 185 and another is 3 core 240? Is there any problem?
You are telling that, okay, I'm just writing your problem. You are telling that you are using from the panel to the motor to run
Yeah.
3 core 185, right?
Yes.
And after that, what happened?
No. Basically, it's okay. But I am using higher side. But is there any problem? Is there any technical problem? Is there?
Technical problem where?
Unbalanced current will be flow from two cable. Is there any technical problem?
मोटर में कहाँ अनबैलेंस होता है? मोटर इज ए बैलेंस लोड.
Hello?
Unbalanced होता है वो trip. It will trip. Motor is a
No.
balance load. Where you are using the that part? Motor is a balance load. If the unbalance is there, it will overheat.
Balance
Efficiency will reduce.
not motor load is unbalanced. Because of cable, is there any technical problem?
Which cable? Just tell me once
There
again.
are two
You
cables,
are telling
two incoming cables from motor.
two incoming cable from where?
From MCC to motor.
MCC motor. One cable is 2 run. Suppose 3 core 185, right?
Yes, and one cable is 3 core 240.
So what are you telling exactly?
Actually, is there any current तो दोनों केबल में जाएगा.
हाँ, बिल्कुल
तो
जाएगा.
जो लो रेजिस्टेंस होगा आपका मतलब है जो केबल मान लीजिए जो जिसका विड्थ स्क्वायर एमएम ज्यादा है तो लो रेजिस्टेंस पाथ है तो उसमें करंट क्या सिमिलर दोनों के ऊपर में लोड आएगा केबल के ऊपर में. My question is that.
Sir, use Kirchhoff's current law. Both cables will carry same current.
But whether he hasn't mentioned whether the size of the cable is same in the two runs.
Yes,
Is
he
it
has
so?
told that the size of the cable is it's same for the two
runs, right?
both
Okay.
cables. So
Okay,
definitely
as per
current will be
Kirchhoff's-
If different
divided.
size,
It will be divided.
if different size is there, is there any technical issue?
Okay, he's asking that. That's what I got the query. The two runs are different sizes. Cable laid for two runs are
Yes,
two different
definitely.
sizes.
In that case, your current carrying capacity will be as per the cross section only.
Cross section only.
Yes.
Okay. So there there is asking unbalanced.
But in this case, I will not suggest you to do two different run for the motor
Yeah,
cable. Okay, I will tell you the reason.
But
Yeah,
I know.
Reason I will tell you.
normally
Suppose
it
the fault
happens.
will occur on one cable, then that cable will burst, and the remaining cable will not be able to supply current. So for the
Yes.
short circuit, I'm just suggesting you. See, this was the comment which we have got from one my client that he is told in the worst
No,
condition.
I know, sir. Normally, we in design section we can't use different cable, but in
Yes,
emergency cases we can use or not.
you
Is there
can
any
use,
technical
but
issue?
the thing is, it will be current will be divided based on the cross
Yes,
section.
yes, that's what it is. Okay, sir. Okay.
Okay.
Okay. This was the my current requirement. So I was selecting 151 ampere. Okay. So 3 core 50 square cable is enough. Now the second thing is the voltage drop. As I told that each cable is having some certain length, and because of that, and my load should be able to supply to get some required voltage. Otherwise, what will happen? The high current will flow, and the efficiency of the load will decrease. So the voltage drop criteria should also be satisfied. Remember, okay, so the general condition is 5% running and 15% starting is the criteria. Okay. In the running condition, criteria is 5% voltage drop. If the meaning of this is up to the load, it should be 5% up to the load, not from the starting. And for the starting, it is 15%. So I'm just assuming one condition. It is a transform which is supplying which is supplying the power to the LV switchboard, then from switchboard to the motor. Then this board is supplying one to the panel and then to the motor. So the thing is, 5% up to the load. See, this motor also wants 5%. So suppose I have considered transformer to the panel 0.5%. So the margin available for this motor will be 4.5%. Okay. And for this motor, if I am selecting 0.5 here, then here I will select 1.5 and remaining will be 3%. See, I will keep basically higher margin for the load so that more margin is available for me because the length is high. Here the length is small. So that's why I can accommodate it in the lower voltage. But overall should be 5% only. It's a overall. Remember, it's a overall. So remaining voltage drop should be considered accordingly. Okay. Clear? It's a overall voltage drop. Clear? Or any question on this?
The voltage will be drop. We have to consider 2.3 maximum percentage of voltage drop is
मैक्सिमम सी इसका भी देखो, अब मैं बताता हूँ कि ये 5% आता कहाँ से, ठीक है. You have to first look at your design criteria. What actually the voltage variation is. Okay.
Okay.
If your design criteria is saying 14 plus minus 5%, means client is telling this much is the voltage drop. So the total voltage drop up to the motor will be this one with the criteria, means 5% only you can allow. If your voltage drop variation is 6%, then you can go for the 6%.
Okay, sir.
Okay, means your cable should be able to supply. So that's why this standard is made general practice, but it is coming from here. Okay. So you can basically.
And the starting current, you have written that 8.4 times.
No,
Normally,
I will come to that part. No, I will come to that part. Basically, it is depending on the efficiency class. In the modern days, i3 motors are available, so that are having the high starting current. Okay, that will
normally dual and dual it takes 6 times.
Basically you are talking about the i2 motor or the that motor is having the low starting current. Okay, it is inclusive of all the tolerance. Okay. So in the modern who can see, currently these motors are also available. If your motor is i3 and you are not having any data, I am telling, if you are not having data and your motor is i3, then current can go up to this.
Okay.
This
Maximum.
is inclusive of the tolerance.
Okay.
So for the cable sizing, you can assume like this. For the LB, you can select 8.4, and for the ST 6 times.
Okay.
Okay, so this is the voltage drop criteria is understood how this is coming, and this is the overall voltage drop. Okay, so here you can see I am sizing from panel to the motor. So the limit is 4.5%. So I will put everything in the formula √3 IL R cos phi X sin phi. See, my requirement is voltage drop. Voltage drop is I equal to I into R. It is a AC, so I into Z. So Z will be R cos phi plus X sin phi. It is a 3-phase, so then definitely multiply by 3, √3. If it is a percentage voltage drop, I will divide the same with the voltage. So this formula is only explode here. If my load is single phase, then it will be 2 IL. Instead of √3, it will be 2. Okay.
Okay.
So like this we can do. So I am putting everything in the formula. It is coming 2.32. My requirement is 4.5. So definitely it is meeting my criteria. Now the second criteria is the starting current. Starting current, I am assuming that my motor is i3 and including tolerance, this much is the current, this much is the starting current. So 8.4. So current multiplied by 8.4. So starting power factor, my 0.2, and this is the sin phi. So after putting everything in the formula, it is coming 8.75. My limitation is 15%, and it is coming only 8 points. So I can say that considering everything, considering the first and second step, I can say that my cable is 3-core 50 square. Okay. So my both the criteria, see, all the criteria should be satisfied. Okay, clear?
Okay.
Hello. It's clear?
Yes, sir. Yes.
Yes, sir.
Okay, that's
Resistance Impedance you taken from catalog, right?
See, impedance I have divided basically the resistance and reactance. It is still available in the catalog. Remember,
Resistance and reactance will be available.
whenever I am passing the AC current, I will do the AC resistance. Whenever I have the DC current, I will do the DC resistance. So that this is available here. Okay. It is multi-core copper armored cable. Okay. And 70 square and resistance is 0.3210. So same I have mentioned here. One minute, let me check once again. Okay, this is for the 4 core I have taken, single core I have taken 0.3210. 0.3210. Okay, reactance is what? 0.0771. Copper conductor. Yes, 0.0771. So it is coming also. Oh, sorry, I have
That is, I think, for XLPA.
no, yes, I have used a different catalog that for the XLP.
XLPA, that is.
Yeah, currently I'm using the PVC
PVC, you are using PVC. That's the reason.
0.0771. Anyway, 0.0. So it is coming 1.64. So anyway, it is meeting my requirement.
Okay.
No problem with this. So based on that, I can size any cable. Okay. I should only understand the condition. Now I'm taking different example. Suppose it's a transformer which is having 2.5 MVA load. So current is this. My rating is this. I will divide it with the rating. So it is coming 6090 current. So I will go to the catalog. See, it's a transformer, so I can go for the N 4 core or the sorry. Generally, the current will be high. So I will use a single core cable. Okay. So I will go to the single core cable catalog. Busted also I can use. The busted I should use because
This
we
cable,
don't terminate.
when transformer is the load, then we are taking from the tapping point to transformer input. The cable sizing we are doing for is from the tapping point
Principal
to the,
tape only.
sorry.
Principal tape only. From the transformer secondary to the panel. Transformer secondary. See, I am sizing for the transformer secondary, right? This is the load. So from transformer secondary to the panel, this cable I am sizing.
Okay.
This
Okay,
cable I
yeah.
am taking. Okay, so my requirement is 6393. And if I look at the catalog, I can see that currently it's a copper cable. So I will again then see the copper cable catalog. Single core copper armored. So my maximum cross section available 630 and it is 660. So I will divide this current with the 660. So you can see I require 10 runs, right? So I can use 10 runs, single core 630 square. 10 runs means 10 for R, 10 for Y, 10 for B. And if your neutral is half, then 5. 5 runs for the neutral. If it is full, then no, or 10 for that. So basically 35 runs. 35 runs single core. Okay. Combining all the runs. Combining all the phases. Okay. The next condition is the running condition. So basically the formula will remain same. I will put everything in the column. Here the runs are 12, 12 numbers in each phase. So not 12, it's a 10. So all the things have been put here. Okay, this is the AC resistance. So 630 is current. I will see the current. This is the single core aluminum, multi-core copper. Single core copper. Okay, my cable is 630 square mm, so 0.0401. 0.0401. Reactance is what? 0.0833. 0.0833. So it is coming 0.57. See, from transformer to the panel, I can go for the 1% as well, because here you can see it is coming only 2%. So I'm having more margin available here, right? So I can say that I can select here 1 as well. Here 1 and here it is the 4. Okay, so it is coming within my the requirement. So I can say that I can select single को 630 square mm 35 runs. Clear? Hello.
So you have increased the size of the cable from
See, the cross section requirement is high, right? Yes. Why? See, I need to increase the cross section, right?
yes,
It's a higher current. My
yes,
small cross section cannot take that.
yes, okay.
Let's say I take a high cross section, and this is the maximum cross section available in that. Remember one thing, up to 630 square mm, we can go for the 3 core as well, or the 4 core. After 630, I should use single core,
core, okay.
because it difficult to bend that multi-core cable.
Hmm.
So we should think like that. If your specs is selling there, see, sometimes in the EL specs you will see that that the client is allowing up to 300 square mm multi-core, and after that it is asking for the
Single.
single core.
Single core, yes, yes. Hmm.
So
So
termination it is elite.
yeah. So this is we should look look like that as well. Okay. Basically, we should see all the specs, then only we should size the cable. So this is the philosophy for sizing the cable for LV cable. Any question on this LV cable sizing? If you know this, you can size any LV cable. Okay. Clear?
Yes, sir. Fine for me.
Excuse me, sir.
Hmm.
Sir, can you explain on the how to take the voltage drop once more? That I have the confusion.
Okay.
Yeah.
Basically, I have told that in the running condition, voltage drop limit is 5%. In starting, it is 15%. Starting
Okay.
means if your load is having the starting nature, means the rotating part, then the limitation is 15%. The meaning of this is up to the load, it should be 5%. So suppose I am having a load which is supplied from the motor, from the transformer. Then you can see from the transformer to the switchboard, then switchboard to the motor. So
Okay.
there are two things are available. One is switchboard, second motor. So if I'm taking, so you can see that I have to divide the 5% voltage drop into some different percentage. So
Okay.
suppose I
Different
am
area we have
taking
to from
yes,
different. Okay.
but overall it will be 5%.
Oh, okay.
Thing is
Okay.
overall.
Uh-huh.
I can see that divided in my hand, but remember my my motor requirement is full voltage. This I cannot change. Overall should be the 5% only.
Okay. 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 Okay.
Okay, shall I move to the ST cable sizing?
Yes, sir.
Yes, yes.
Okay, so ST cable sizing is very much simpler as compared to the LV. If you can calculate it even on the calculator. Okay, so ST cable sizing, as I told that, it depending on the two criteria, current and the fault level. If you are able to determine correctly the fault level, means minimum cross section, your cable sizing is done. So ST cable sizing, suppose I am having a motor load which is of 6.6 kV. So current will be 102.91, and this is the my current requirement from the cable 189. Second criteria is the minimum cross section. The formula for this is I root T upon K. I is the fault level, T is the fault clearing time, and K is the constant. Okay. Constant value is mentioned in the IS 3043, so I have directly taken from here. It is depending on the insulation as well as the conductor. So 94 for aluminum XLP, 143 for copper XLP. Okay. For the motor feeder, I should take 0.25. If it is a bus coupler, then 0.5 second. If your motor is fuse controlled, then it will be 0.01. Okay, this should be the fault clearing time. It's not a standard, it's a general practice. Okay, the only thing is, suppose I am taking it 1 second, means my relay should trip the breaker within 1 second. So this is how this value is coming. Okay, so this is the fault clearing time. Okay, suppose I'm supplying a motor which is having the ST VCB. So therefore that I will take the fault clearing time 0.25 second. Okay, so this is the fault clearing time. So I will put everything in the formula. So fault level, suppose fault level calculation I will tell in the next class, mean tomorrow, how to calculate the fault level. This is also addressed here, but I will tell tomorrow. So I root T upon K, I is the fault level, T is the this 0.25 and divide by K. K is copper, for the copper it is 143. So it is coming 87.4. Okay, we say XL copper. Okay, so you can see my second step is telling my minimum processing should be 95 and this is 189. So I will go to the HC cable catalog. This is the ST cable catalog. Single core XLP. Single core aluminum. Aluminum. 3 core aluminum. There. 3 core copper. Okay. So my requirement is how much? 189. So this 189 I can get from this 35 square mm. No, sorry, this 50 square mm, correct? But my second step is telling then I cannot go below 95. So even if the current requirement is less, but because to fulfill the criteria minimum cross section, I need to select 3 core 95. So that's why I was telling, if you are able to determine the minimum cross section correctly, we can easily size the cable. So you should understand only the minimum cross section, mean the fault clearance time.
This constant K is stand
This
as
is
per the
yeah,
IS.
yes, IS, this is mentioned. I will show you when we will discuss the earthing part. My next topic will be the earthing after this cable. So this is directly mentioned here, and we can also calculate it. Okay, the
Okay.
formula is there. I will also show you that part.
And how about the fault clearing time? Is it as
Yeah,
per the standard only?
yeah. It's not a standard. Will not tell you anything. The thing is, my relay should trip within this time.
Okay.
So if
How
you
we will decide that within 1 second my relationship?
yeah,
How will
this is
set the
verified
criteria for that?
with the relay. This is verified by the relay coordination only. Okay, so just assume this condition. That it is a transformer which is supplying power to the motor, and this is in context a bus coupler. So suppose the fault happens here, then this breaker should trip first, then this, right? So suppose I am taking 0.25 for here. So then remaining 0.25 is a discrimination margin. Mean after 0.25 second, this breaker should trip. So 0.25 plus 0.25, it is 0.5. Then again 0.5 plus 0.25. So it is 0.75. So like this, the time will increase.
Okay, it is based on the coordination there.
Yes, coordination only.
Okay.
So as of now, you can just learn this. That for the bus coupler, I'm taking 0.5 like that.
Okay.
So if you are able to determine the cross section correctly, the ST cable sizing can be done even on the calculator. Okay. If your system is fuse control, means it is having fuse plus contactor, then the fault current, there is no need to determine the minimum cross section because time is very less, 0.01 second. Your fuse will blow in that. Okay, so it's like this. So now the second thing is I have avoided the voltage drop in the ST. So even if you determine the voltage drop, see, you can see the suppose my length is here 300 meter. If I'm determining the voltage drop, so the voltage is high, current is low. So you can see the voltage drop is coming only 0.07. So it is already very less. Suppose my length is 3,500, 3.5 kilometers. Even for this is it is less than 1%, so which is negligible. So that's why we can avoid it. But your
That,
if your
that
length
is
is
the
very
reason.
high,
That is the
yeah,
reason for long lengths we step up the voltage and
yes,
carry
yes,
higher
yes,
voltage
yes,
HV voltages to long
yes,
lengths.
yes, long length. So basically, if your length is very high, then only you should think like this.
Hmm.
You should basically calculate. So, or you can go for the higher voltage, like 11 kV or 6.6 kV, based on the length. Okay. In the LV, I was avoiding the minimum cross section fault level. So in the LV, as you know, we are using the MCB or MCCB, right? This MCB is having the current limiting device. The meaning of this is this is the catalog which is given by the vendor. See, for the 50 kilowatt, suppose I am selecting a MCCB of 125 ampere based on this current, suppose. So I will go to the catalog. 125 ampere MCCB, 50 kilo ampere fault. How much will be the current will flow in the system when the fault will occur? So there is a let through energy curve is provided by the vendor. This is the let through energy curve. Okay. My current requirement is 125. Suppose this is the curve between the fault level and the energy. Okay. This is 25 kilo ampere. Okay, I'm moving ahead with this. Yeah, this is the current. This is for the single phase. This is for the three phase. Suppose my current is 125. My breaker is 125 three phase. So my fault, suppose my fault is 50. So 10, 20, 30, 40, 50. So corresponding to this fault level, how much energy will flow? This will be this. So it is 0.8, right? 0.8 into 10 to the power 6. So this much energy will flow in the system. It's okay. This 0.8 into 10 to the power 6. So corresponding energy means the ice quality value will be this is the ice quality value, which will flow when this MC will trip. So ice quality is 0.8 into 10 to the power 6. Okay, so this is the energy which will flow. My formula was I root T upon K. This is ice quality, right? So I will take the under root of this. So it is this under root. As my cable is copper, so I will divide it with the 143. So you can see that my cross section is coming only 6.255. Means only 10 square cable I want for this fault level. So that's why I can avoid that. Okay. So with by considering this thing, I can say that I can avoid the minimum cross section in case of LT cable. Because my switchgear is the current limiting device, which will trip much before the fault level. So this fault level curve is provided by the vendor, which I can see. This curve is called the let through energy curve. Means as per the fault level, how much current will flow, which I can verify from here. Okay. This is the curve between the kilo ampere and this energy. Clear? So that's why I was telling that I can avoid the minimum cross section in case of LU. So if you understand this criteria correctly, you can size any cable, any HT cable, LT cable, whatever. Clear? Hello. Hello. Can you hear me?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
So I hope this is clear.
Yes,
If there is,
sir.
so I am just giving you one exercise. This is a 25 MVA transformer. The primary voltage is 33, secondary 6.6, and the fault table is this. You have to size the cable for the primary as well as the secondary of the transformer.
We have to do it now or later?
No, you can do it later. Just show me only to tell me tomorrow only. It's
What will
just
be
for
the
the
transformer
practice
rating?
only. Huh?
Transformer rating just
25 MVA.
25 MB. Okay.
Is the
So
same
this is
Excel
just
sheet you have
you
shared
can
us
do
now?
anywhere. You can do anywhere wherever you want. It's for your practice only. So what I am doing, I am just sharing it to you.
The main thing is main inputs required is length.
Length you can assume here. It's a ST,
Okay.
so you can assume 250 meter.
Okay.
Nothing will happen with the voltage drop because it's a ST.
Yes, sir.
Okay, so nothing will happen. Don't worry about this. So I am sharing this cable sizing calculation. So I hope this part is clear. If this part is clear, I will tell you the different thing tomorrow, which is the fault level calculation. So this will also be used when we will size when to see how to determine the fault level. Fault level we will see from the EHV as well. So I will tell you when to get this. Okay. So this is the Excel sheet and all the remaining catalog I have already shared. So just do this. I think you can do it easily. Right? If there are any questions, you can ask me. Okay, it's clear now.
Yes, sir.
One question I want to ask.
Yes.
If there is a hume pipe and we laid one HT cable in the hume pipe, can we lay LV cable in the same hume pipe?
No. In the same pipe?
Yes, sir.
No.
Minimum 300 gap will be there.
Yeah, big C. Just understand one thing. The thing is voltage, right? One is ST voltage, one is LV voltage, right? So ST voltage, the magnetic field will be high, right? In the LT voltage, the magnetic field will be less. So what will happen if you suppose put it in the same pipe? So what will happen? Derating will occur. Derating means current will flow from the lower high voltage to low voltage. Means the field will flow from ST to LT. So that will distort the LT cable signal. So that's why we cannot take that.
Okay.
Okay, so we should think like that. Okay, clear?
Distorted means the current conducting will be disturbed, or what way we can understand it?
The rating means current rating will reduce. Heating will be there.
Okay, so due to magnetic field,
Yeah.
LV cable may get heated up in very short time.
Because LC current basically from the high to low. So definitely my ST cable will be the same signal. But my in case of LV, it will distorted. Just like suppose you are having the LV and the instrumentation, then only instrumentation signal will be distorted, right? The same
Yes.
will be happen for the lower voltage.
Lower voltage and current. Okay.
Yes. So the distortion will happen. That's why we cannot do that. Okay.
Okay, sir.
I hope this part is clear. My next topic will be the fault level calculation. This is also your next topic. So it is mentioned in this Excel sheet as well. But please do this cable sizing. If this is understood, you can size any cable. Okay, this will be my second topic, which I will explain tomorrow. Okay. Any further question?
At what time, sir, tomorrow?
Same, 8 p.m. Tomorrow I was having some work, so that's why this happened. But
Okay.
tomorrow it will be 8 p.m. only. Okay. I have already shared the link, so you will get it. Anyway. Okay, so this is the link. Anyway, if there is no question, so I think I can close the session, right?
Yes.
Okay, sir.
Okay, thank you everyone. We will meet tomorrow at 8 p.m.
Okay.
Okay, sir.
Okay, thank you everyone.
Okay.
So there is no question from the yesterday query, so I am starting the new thing. Okay, just for time.
Excuse me, sir. I have one doubt, sir, regarding yesterday.
Mhm.
Uh, Actually, I just go through that problem. Okay. Actually, uh, in that case, there's a two voltage, primary voltage and the secondary voltage. Okay. The primary voltage is 33 kVA and the secondary voltage is 6.6 kVA. Is it, sir?
Mhm.
Uh,
Mhm.
so actually, according to the formula, in 33 kVA, actually in 33 kVA, the side current will be nearly 439 amps.
Hmm.
And in the secondary side, it's 2000,
2500.
2000 something.
Uh,
Okay.
2200 something.
Okay. Sir, actually, well, in 413 in primary side, actually we have to use unearthed cable. Is it, sir?
We have to use.
Unearthed 33 kVA cable. You know.
See, I have not told you that any type of grounding.
Okay.
So if the thing is, if your system is grounded through NGR or it is unearthed. Okay, if you are asking this, so I am explaining you. The thing is, here you can see it is grounded through the NGR. If it is grounded through the NGR or it is ungrounded, then secondary cable will be considered as unearthed. All secondary cable, not the primary cable.
The primary cable we have to consider unearthed cable.
Earth, no, primary cable will be unearthed only when your source is not grounded.
Not grounded. Okay.
See, here there is no information for the source. So right now I will suggest you not to consider that part.
Okay. In secondary side,
See, if you look at closely, the 33 kV will always be solidly grounded. So you can consider the earth cable for the primary. Okay.
okay.
And so that's why I'm telling there is no information, but the general standard is it will be grounded through the solid electrode. So we can consider earth cable.
Okay. 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 Okay.
Anupasavade.
Sir, actually, the NGR means neutral
Grounding resistor.
neutral grounding resistor.
Basically, we are inserting the register.
Inside in the register. Okay, a resistor. Okay.
So this NGR basically considered as an unearthed system because this works only for the short time.
Okay.
It's for 400 ampere for 10 seconds. Means in this time, your relay should trip. If that is not tripped, then your register will blow and it will be the open circuit.
Okay.
Getting my point?
Yeah.
I'm telling this is a register. So suppose it is a 400 ampere per 10 means my relay in the secondary or the primary should trip within 10 seconds. If that is not 10 seconds, then the register will blow and it will behave as an open circuit. So no, it will behave as an unearthed system. So that's why we are considering it as an unearthed system because this NGR works only for the shorter time.
Okay.
For the 10 second, it is an earth system. But if the relay will not trip anyhow, then it will be the unearthed system.
Okay.
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 Any further question? Hello, any further question?
Actually, sir, can you give a demonstration regarding this problem? Because
See, this thing will come in the ETAP part. In the ETAP, you will visualize this.
Okay.
that this much ampere is current and this is on our system. Okay. Whatever I'm telling you right now, this will come after the lightning protection. So just wait for some time. This will be visualized in the software.
Okay.
Okay. So just wait for some time only.
Okay.
Further, you will get this software from the advance. I will inform you 1 week before, so you will get it. Okay, so shall I move further or any further question is there? Okay, so we have assumed some fault level yesterday. So today we will discuss about the how to calculate the fault current. Does anyone know that what will be the highest value of the fault current in the system? Is it three phase or LG or double LG or LL fault? Which fault is the maximum value? Which fault is having the maximum value in the system? Is it three phase fault or it is line to ground fault or it is L2L fault? Which fault?
Line to ground.
So you are telling line to ground is the maximum fault. Maximum
Yes, sir.
means I am talking about the magnitude, not the percentage that of chances of line to ground is high. I am asking the magnitude.
Okay.
Line to ground, see the percentage high because it happens most of the time. So it happening is more, but I am talking about the magnitude, which fault is high. Okay, so it is basically the three-phase fault, which is the maximum in the system. So all the switch gates are designed considering this fault current. Okay, so this fault is basically used for the switch gate sizing or considering the switch gate selection, bus bar, everything will be considered based on this cross section, cable cross section, everything will be done based on this. Okay.
Okay.
Now, the thing is how to determine the fault current. The current is basically the simple formula is V upon Z. If it is three phase, V upon root 3Z. So simple Ohm's law is there. Voltage divide the impedance, divide the voltage with the impedance. So whatever system is having the impedance, we will use this and divide it with the voltage. Okay. Now, how do we do this? I am just assuming one condition here. See, this is the grid, which is 33 kV and providing supply to the transformer. And after the transformer, there is a motor load, which is connected to some motors. So connected to some cables. Okay, so this is just one SLD I have assumed. So anyone has done the fault table calculation earlier?
No, sir.
No, sir.
No idea about that as well. Okay, so first I will tell you the detailed analysis, then I will tell you the thumb rule. Okay, in this condition, you can see I am getting the supply from the grid. The grid voltage is 33 kV, and basically we require the input from the client that how much fault current is. This is RCs, right? It's for RCs, right? Who has called me right now? Hello. Hello. Hello.
Yes, sir.
Just now I've got call from Ashish, right? Ashish, you have called me right now. Just now. Ashish, can you hear me? Anyway, he is not replying, so I cannot tell anything now. Okay, all the links are available. Whatever we are discussing, this will be stored in this meeting ID. So you can download it later as well.
So
Okay.
one request is that
हाँ बोलो.
सर इसका लिंक शेयर करिए सर। हर बार मतलब क्या लैपटॉप से भी कनेक्ट कर सकते हैं, ये मोबाइल से कनेक्ट करना पड़ता है लिंक नहीं आया तो।
नहीं, कौन सा लिंक नहीं आता है? जूम पर मैं तो लिंक बनाकर ही भेजता हूँ। क्लास जब शुरू होती है, जैसे शेड्यूल
आज
पे
का नहीं
जाओगे
आया
ना।
था सर।
अरे तो ये तो मैंने 1 हफ्ते पहले बना के भेज दिया था लिंक
कल का आया
तो।
था सर, 20 तारीख का। 21 तारीख का नहीं आया था।
नहीं नहीं, कल मैंने थोड़ा सा एडिट किया था, इसलिए तुमको लगा होगा कि नहीं आया, लेकिन वो बाद में मैंने ठीक कर दिया था। ठीक है। वो
ओके
ना
ओके।
दिखता है थोड़ा, मैंने एडिट किया था, इसलिए तो वो तुमको दिख रहा होगा। बेसिकली क्या, मैंने अगले हफ्ते की भी मैंने कर दिया है। ठीक है, तो वो तो मैंने सब कर दिया, तुमको दिखेगा। आई कैन हियर यू सर बट यू कैन नॉट हियर मी। ओके। So all the I have already made of all these things. So this you can see later as well. So this is the 27. For the 27 also I made the schedule, and for this 28 also I have scheduled. So this I
ओके
have already done 1 week before. So you will see this later. Anyway, so this is my grid supply, which is 33 kV, which is supplying power to the transformer. Then after transformer, there is the motor load. So we have to determine the fault here at bus 2 and at motor terminal. So you can see here how many impedance are there. This is the source impedance, this is transformer impedance, and this is the say cable impedance. So if I get all the things, I can use this impedance for determining the fault current. So here I am getting the 33 kV supply and the current fault current which is coming from the sources. This is the fault MVA which is coming from the source. Means this input is basically required from the client. How much fault MVA is there at their side? Means from the grid, how much fault current is coming. So this is the fault MVA rating. So based on that, I can determine the current. So √3 VI. So simple formula is there. √3 VI. So I will get the fault current at this point. Okay, this is bus 1. Okay, this is at the grid side. Okay. Only one. Now after this, there is a transformer. So transformer is also having the impedance, which is called the percentage impedance. Percentage impedance means this is the, anyone know the percentage impedance? Basically, this is used for determining the fault current value. If the value percentage impedance is high, definitely current will be low. So fault current will be low. If the percentage impedance is low, then it will be the fault current will be high. But what is happening? Suppose my percentage impedance is high, then because of the impedance, the losses in the transformer will be more. Because IZ. So this will increase the losses in the transformer, means the voltage drop in the transformer will increase. Okay, this percentage impedance is also mentioned in the IEC. You can directly refer this catalog, this table, through which you can see the percentage impedance based on the transformer rating. So I will share you this thing. Percentage impedance value should be minimum, because at minimum impedance, fault level may be high, but thing is the voltage drop in the transformer will be less. Okay, so we should use the minimum only. Okay, then at the same time, suppose I want to increase the impedance for reducing the fault current, then I need to ask to the vendor whether it is possible to get more impedance in that or not. Okay, because it is increasing the loss. So vendor has to confirm whether this minimum loss is possible, even if the percentage impedance is high. So this value we can get it. So this is my transformer. Primary voltage 33 kV, secondary 6.6, and this is the percentage impedance, and this is the MVA rating. So first is the source impedance. Suppose I need to determine the fault current at this bus, then how many impedance are there? Source impedance plus transformer impedance, right? So source impedance, the formula is base MVA divided by fault MVA. Base MVA is the transformer MVA, fault MVA is the fault current which is coming from the source. So this is in per unit. Now next is the transformer impedance. So it is 8% or 8 divided by 100. So total impedance will be source impedance plus transformer impedance. Since this is in the per unit, so I will use convert it in the ohm. So the formula is percentage impedance divided by 100 into kV square upon MVA. After using this, it will come in some ohm. This is ohm because I have convert this per unit value into the ohm. So now the fault current will be what? V upon root 3 Z. So voltage is 6.6 kV, root 3 into Z. So simple, the fault current will come at bus 2. You are getting my point. I am just adding the impedance of source plus transformer, then just converting it in the ohm and using the secondary voltage for determining the fault at bus 2. Okay, clear? Please ask your question so that I will understand.
सर 1500 MVA और वो फॉल्ट करंट कहाँ से लिया सर?
ये तो हमको सोर्स क्लाइंट से चाहिए होता है कि अगर इफ समवन इज प्रोवाइडिंग अस द supply, then he will tell how much fault level is coming from the source. So this input is required from the client. Okay, so
Okay,
this
sir.
is the input. This is the input. Suppose client is using the fault level at the source side for 40 kilometer and the voltage 30 degrees. So we can also calculate. So root 3 into the voltage. So this
Got it,
this
sir.
one will, so this one is the fault MVA, but this is given by the client only. This is in our hand, but this is the input requirement. Okay. So what I have
Yes,
done,
sir.
I have just added source impedance and transformer impedance. Now suppose I have to determine the fault at motor location. So how many impedance? Source, transformer plus cable. These three impedance will be there. So the cable impedance will be Rx. I can take from the catalog, and this is the length. So total impedance will be R square plus X square. This will be the cable impedance. Then I will add this cable impedance with the remaining two impedance. So this is in ohm, and the fault current will be the V upon root 3 Z. But here, okay, remember one more thing. If any load which is rotating in the nature, it contribute to the fault current. Because just like a motor is having a residual magnetic field, so it is contributing to the fault current. Means it will generate the fault current. So for the motor, fault current will be the maximum fault current will be the starting current of the motor. So this is my 560 kilowatt motor. So the current will be this one. So starting current will be 6 times of this. This is the current contribution by this motor, and this is the current contribution by this motor. So both the current will be added. Means the current coming from the source plus the motor current. So 16.18 plus 0.35 plus 0.49. So it is coming 17.02. As per IEC, if we want to determine the maximum fault, then just multiply with the 1.1. We will get the maximum fault current. Okay. Here I have just added one more thing. I have added the motor control because motor also contribute to the fault current. Okay, because it is having the residual magnetic field. Suppose the fault happens here, then which fault current will come from the source plus current will come from the motor. So all the contribution will be added because the voltage at that point is 0, and all the remaining equipment will be on the higher voltage. So that's why, because the potential difference is current flows. So the same thing I have done here. I have just added the current from the motor plus this is the current from the source. So all the things are added and getting the required fault level. Okay. Okay, please ask your question. I am explaining again. Suppose I have to determine the fault here, then how many impedance are there? This is grid, source impedance, transformer impedance plus cable impedance. Next is the motor contribution. So all the things will be added. So source impedance I have determined, transformer impedance I have determined, then converted in the ohm. This is my cable impedance, which is this. And I am adding the cable impedance with the remaining two impedance, means source impedance plus transformer impedance. So this is coming 0.23, and the current will be V upon root 3 Z. So it's a contribution by this motor and this motor. So both the current contribution will be added because motor also contribute to the fault current. Okay, so this will be the starting current of the motor. So 0.35 for this motor and 0.449 for this motor. So all the currents will be added and I am getting the maximum current value. Okay, 17.02. Something is clear here or nothing? Hello? Hello?
Yes, sir.
Hello.
Shall I move further?
Yes.
Is the concept
Yes.
is just understand the concept and you can do anything. You
Please,
can
sir,
do
repeat.
any calculation.
Please, sir, repeat, sir. I can't hear you because my connection.
You have not heard anything?
No, sir, no. Now, just 2-3 minutes. I'm not able to.
Okay, so this was the, see, I am just assuming one SLD. See, I am getting 33 kV supply from the grid. And
Yes.
after this, there is a transformer which is supplying power to the motor. The formula for the current is V upon Z. So just
Yes.
use the impedance and divide it with the, divide the impedance with the voltage. Just simple Ohm's law. So I will determine the impedance here and use the corresponding voltage. Suppose I need to determine the fault level at motor terminal. So how many impedance are there here? Just source impedance, is transformer impedance plus cable impedance. Okay. So this is the source impedance, the transformer impedance plus the cable impedance. Source impedance, the formula is base MVA divided by fault area. This is the transformer impedance. This is the transfer percentage impedance. So both the impedance will be added and this is in the per unit. I am converting this per unit in the ohm. The formula is percentage impedance divided by 100 into kV square upon MVA. So this much will be the fault current will be V upon root 3Z. So B is the 6.6 kV root 3Z. So suppose I need to determine the fault and motor terminal. So in this impedance, I will add the cable impedance also. So my cable impedance is this R and X, and this is the length. So total impedance will be the R square plus X square. This is the cable impedance. Now I will add this cable impedance with the source impedance plus transformer impedance. So this is the impedance which is basically given by, which is basically calculated by adding the source plus transformer plus the cable. So the fault current at the motor terminal will be V upon root 3Z. Here you can see my motor is rotating in the nature, so it also contributes to the fault current because motor is having the natural magnetic field which will contribute to the fault current, and that value will be the not more than the starting current. So I am using the starting current of both the motors. Okay, so this is the 6 times of the current. Here also it is 6 times. So I am adding the this fault current with the motor contribution. So I am getting this fault current value 17.02. Okay, now you got.
Yes, sir. Yes, sir.
Just understand the concept. I am just using the impedance. Then after that it is
सर
Ohm's law. हाँ बोलो.
रेटेड इम्पीडेंस का यूनिट ओम आया सर उसका थोड़ा
ये फॉर्मूला है, इस पर यूनिट को ओम में कन्वर्ट करने के लिए ये ना फॉर्मूला है. ये तो तुमने बीटेक में भी पढ़ा होगा. परसेंटेज इम्पीडेंस में कन्वर्ट करने के लिए परसेंटेज इम्पीडेंस डिवाइड बाय 100 इंटू केवी स्क्वायर पर एमवीए. तो केवी मेरा सेकंड साइड का 6.6 केवी डिवाइड बाय एमवीए. तो इसको बस मैंने ओम में कन्वर्ट किया है.
ओके.
तो ये फॉर्मूला है इसका. इससे मेरा आ गया ओम में तो V अपॉन रूट 3Z. तो सिंपल मैंने वोल्टेज को यूज किया और इम्पीडेंस से
ओके सर
डिवाइड कर दी.
गॉट इट.
सिंपल इज दैट. Now, suppose now I am telling you the thumb rule. Suppose there is a transformer, you need to determine the fault current by that. This is the thumb rule. Just divide the transformer current with the percentage impedance. You will get the fault current. Suppose this my 2 MVA transformer, so current will be this one. I am dividing it with the percentage impedance. So this will be the fault current value. This is the thumb rule. Divide current with the percentage impedance. We will get the current. But remember, this is not a detailed analysis. It can be used as a thumb rule, but it will come same. Okay, but okay, getting my point. This is a thumb rule for determining the fault current. Hello.
ओके सर ये अब थंब रूल ऊपर के जो हमने एग्जांपल ले रहे हैं उसके ऊपर अप्लाई करेंगे तो सेम आता है?
नहीं, इसमें बस ट्रांसफार्मर का ही तुम निकाल सकते हो, बाकी चीजें यूज नहीं होंगी इसमें। जैसे तुम्हें ट्रांसफार्मर का कंट्रीब्यूशन फॉल्ट निकालना तो इतना ही आएगा बस।
ओके ओके सर।
इसमें तुम्हारा कमाई थोड़ा ज्यादा, मतलब इसमें बस इतना ही आता है। थंब रूल है
ये
ना।
जो सर ये जो केबल इम्पीडेंस है सिर्फ ट्रांसफार्मर टू बस है कि मोटर तक जो केबल इम्पीडेंस बताया आपने?
ये मैंने केबल लगाया है पैनल टू द मोटर, तो इतना लिया है मैंने। यहाँ तो मैंने डायरेक्ट कनेक्शन माना हुआ है,
ओके
तो
सर,
यहाँ पे
ठीक।
कोई इम्पीडेंस ही नहीं है। जितनी भी केबल होंगी यहाँ से यहाँ तक की, अगर ये केबल है तो इसका भी इम्पीडेंस ऐड हो जाएगा, वो तो सेम
ठीक है,
रहेगा।
यस यस।
Now I am just assuming some different example. Here there is a DG which is supplying power to the transformer, and on the DG there is a motor load. Okay, so just tell me technically, if I want to determine the fault at bus A, so which impedance I should take? Suppose on the bus A, I need to determine the fault current contribution. So which fault will be added?
Which fault?
Means how we will determine. How I will determine the fault current at bus A.
वो add
स्टार्टिंग
both
करंट ऑफ मोटर प्लस ट्रांसफार्मर फॉल्ट करंट।
add भी both.
Transformer here. Remember, transformer does not contribute to the fault current. It will only what it is actually doing based on the fault current which is coming from the primary side. It is basically stepping up or stepping down. The fault current contribution is done by the DG motor or from the source only. Okay, these are the fault current generator. Transformer is basically based on the impedance. This is creating some value. Okay, so here suppose in the bus A, I need to determine the fault. Then which contribution will come? It is the DG fault current plus motor contribution. So these two current will be added, correct? And this for both the fault current will bulk as a source impedance. So then source, transformer, and then I can determine the fault at here. Suppose this is my 26 megawatt generator. So I am converting it with the MVA. So how I can determine the fault current here? Base MVA divided by, this is the subtransient reactance. So base MVA divided by percentage impedance. In the DG, it is subtransient reactance. So it is 0.2. So fault current will be √3 VI. So this is the fault 162.5 divided with the voltage. So voltage is 11 kV. So this is the fault current contribution by the motor, by the DG. And now this is the motor. So motor current is this one, √3 VI cos phi, and this is the starting current. So both the current, DG current and this current will be added. So at the bus A, what will be the fault level? It will be the addition of the DG fault current plus this motor contribution. So this is the fault current at bus A. Getting my point? And this fault current will work as a source for the transformer. So transformer will basically use it as an input, and based on the transformation ratio, it will change its values in the secondary. But transformer by own is not contributing to the fault current. Transformer is not a generator. Okay. Okay. Hello.
Yes, sir.
Getting my point? It's not a generator, so contribution is governed by the rotating part, which is DG or motor. Tell me whether heater load is generator. Suppose I am using a heater, will it generate the fault current? Hello.
Sir,
Heater,
repeat question.
I am asking, instead of motor, suppose it's a heater. So will heater contribute to the fault current? Heater is basically a resistive load which does
No,
not
Yes.
take
sir.
any starting current. Okay. So it will
Okay.
not contribute any fault current. So this is static load. There is no rotating part in the heater. That's why it will not contribute any fault current. Okay. So now this is the fault current at the input side. So the fault MVA will be what? √3 into fault current into the voltage. Okay. Source impedance will be base MVA divided by fault MVA. Base MVA is transformer MVA. The secondary voltage is 60. Transformer MVA is 60 MVA, and base MVA is this. Okay. My transformer impedance is 0.1125. So both the impedance will be added. So here I have added the source impedance plus transformer impedance. Now I'm converting in the ohm. So kV square upon MVA. So this will be converted into the ohm. Now the simple thumb rule is V upon √3Z. So this is 66 kV at the secondary line, dividing it with the voltage for the impedance. So this is the fault level at bus B. Okay, getting my point? Hello. Basically, this will work as a source. Now, source impedance will be base MVA divided by fault base MVA divided by fault MVA. Now, I will convert. Now, I will add here the transformer impedance, which is this one, 12.5. Now, both the impedance will be added here. Okay, this is transformer impedance plus source impedance, and here it is converted into the ohm because we upon √3Z, that is in ohm. So, based on that, I can determine the fault current. Okay.
Okay, sir.
I hope
Okay,
this
sir.
is clear. Okay, now this is the third exercise. Just assume these are the 3 DGs. I need to determine the fault at bus 2. So just tell me what will be the fault current value at bus 2. Just think logically. It is the 3 DG are supplying power to the bus 2, and which will be the what is the fault by value of the fault current at bus 2. Will it be the addition of the 3 DGs, or it will be the contribution by only by one DG? Hello.
Mm.
See, all the DG will run in synchronization, so contribution from all the DG will be added here. So I have done the same here. I have determined the fault current by 1 DG, then multiplying with the 3. Okay. Here the same thing I have done. So suppose now the second thing is, suppose this bus coupler is off and in one condition it is on. Suppose at bus 2 the fault current is X. What will be the bus fault level at bus 3 when the bus coupler is open or when bus coupler is off, or the on condition? So just tell me the how we can determine the fault at bus 3 when the bus coupler is on, or second condition it is in off condition.
When it is up, it is the same.
Yes.
Bus 2.
Yes. Or when it is on.
Then
When it is on means in that condition, the transformer
We
and
have
DC
to-
port will be on the
Source
synchronization.
and transformer.
So I have to add the this fault
The
current plus
transfer-
this fault current, right?
Yes.
And now here it will be the motor contribution as well. So all
Yes,
the
sir.
three contribution will be added, right?
Yes, sir.
Yes, sir.
Right? I hope you are getting this.
Yes, sir.
Yes, sir.
Okay. If you are really getting this, just do this exercise. Means I want the fault current at bus 3 when all the DGs are in running condition and bus coupler is off in one condition, and in second condition bus coupler is on. Okay, if you understand this really, then you can easily do this. I hope you are understanding just understand the concept. You can easily do this. Okay, after this, my next topic will be the earthing. If you are confident about these two topics, means the cable and the fault level, we can do the earthing. Okay, so are you getting this fault level calculation? What I am doing, I am sharing this worksheet.
This fault current will visualize in ETAP also.
Yes, yes. I am just right now, I am telling you the manual. Okay.
Yes, sir.
So because ETAB is a licensed version, so most of the companies are not having this. So we should know it in the manual as well. So just understand the concept only. This can be seen from the ETAB as well. But as of now, you should remember the thumb rule. Multiply the current, just divide current with
Yes,
the
sir.
percentage impedance. You can get the value of the fault current. Transformer current divided with the percentage impedance. Okay. Do you want to ask any question on this fault current calculation? Anyone wants to ask? Or any doubt is there till now? Doubt will be there, definitely, I know. But anyone wants to ask or you want to practice right now? Okay, I am suggesting you to just do practice, and you can
Okay.
ask me over Skype, over the Zoom as well, if you are facing any doubt. Okay, so just do this exercise once, just only one time. You will basically understand the concept. Okay, then you can easily do this. Okay, so just do this exercise and then come back to me. One condition is bus coupler is off, and second condition bus coupler is on. Okay, just do this exercise. If you can do this easily, then you can calculate current at anywhere. This will be verified for the ETAB as well, but later after lightning part. Okay, so I have already shared this part. If there is no question is there. Hello, any question is there from this calculation?
No, sir.
Okay, so if there is no question, so I have already shared this thing. My next topic will be the earthing, which we will discuss in my next class.